there's a way of defining angle measurements that is crucial in the work in trigonometry, and also looking at trigonometric functions when we want to graph them and that sort of thing. And this is the idea of a radian measure. Now, the difference between a radian measure and a degree measure is our degree measure actually measures our rotation from the initial side to the terminal side by taking a circle and cutting it up into 360 equal parts, each one called a degree, and then looking at that span. With a radian measure, we're actually defining it as the length of an arc that it's equal to. And so it's a real numerical value instead of just a rotational value. And this is what lends itself to being able to be useful in graphing trigonometric functions and other applications. Now, the definition of a radian is 1 radian is a measure of the central angle subtended by an arc of length r on a circle with a radius of r. So a radian is the length of a radius. When I look at each of these two circles that I've drawn, in each of these, the angle that's drawn is an angle measurement of 1 radian, because for each of them, the value that you look at for the radius of the circle, if you took that length and had it measured out on a string, so example, take this string and measure out from the center of the circle to the circle itself, and then lay that following the curvature of the circle, that exact arc length then marking the two sides of where that arc length starts and stops. If that's exactly the same as 1 radius for that size of the circle, that's called an angle measurement. That central angle is called an angle measurement of 1 radian. So here, again, I have a different size circle, so it has a different size radius. But if I take my string and I measure the length of the radius and then follow the curvature of the circle around, I get the length of the radius along the edge of that circle. If that's exactly the same as the length of the radius, then that central angle theta has a measure of 1 radian. So a radian is the length of the radius, and you lay it out around the circle. Now, relationship between the arc that's subtended by the central angle and the central angle itself, is that theta is just equal to s divided by r, the length of the arc divided by the length of the radius. And remember that if the length of the arc is the length of the radius, then I would have r divided by r, which is 1 radian, which we discussed over here. Multiplying both sides of this equation by r gives me that the length of an arc of a circle is equal to the radius times the central angle, as long as your central angle is measured in radians. You have to have that real number measurement for that. Now, as we go through, we'll look also at the connection of how we can look at converting from degree measurement to radian measurement and vice versa. So we'll be able to answer these later on for both degrees and radians, but right now we're focusing on this new measurement called the radian. So the question here is, find the radian measure of a central angle subtended by an arc of 15 centimeters on a circle with a radius of 10 centimeters. So here the units are the same. The arc length is s and the radius is r. So we're going to use, looking for our central angle theta, we're going to take our arc length of 15 centimeters and we're going to divide it by our radius length of 10 centimeters. The units match, so they remove as common factors. And I also have a common factor of 5 top and bottom, so I'll get that my theta is equal to 3/2 radians for that. So I would actually, for the central angle for that, be able to kind of visualize it looking at, say, this being my start. If this is my radius, and let's say that was a 10 centimeter circle, then it would be 1.5 of these radians that you would get for the measurement of the arc that you would have in terms of that central angle that you would draw. Now, let's remember something from geometry. Remember that the circumference of a circle is 2 pi r. So 2 pi times the radius. So if we have a circle, and let's say that we have it superimposed on the xy plane, and I start at the positive x-axis on the circle, and whatever the radius is, so some of you have maybe talked a little bit or been in other classes where they've maybe discussed the unit circle before. We're not talking about the unit circle quite yet. The unit circle specifically is a circle whose radius is 1. Here we're talking about a circle, any circle with a specific given radius of r. So if I have my radius of r, and I start at the circle and I go all the way around and end up back on the circle again at my starting point, the entire distance around the circle is called the circumference, and the circumference is equal to 2 pi times r. Well, r as a length measurement, in then thinking about laying the r out along the circle, well, laying it out along the circle and then finding the central angle that subtends that arc is a radian. So if I look at this situation that the circumference is 2 pi times r, and laying the radiuses out are giving me my radians, then for any given circle, there are 2 pi radians around the outside edge of the circle. So around the circle, you have 2 pi radians. And if I have my trig angle in standard position, where the vertex is at the origin and the initial side is the positive x-axis, then when I do my terminal side, if I went all the way around from the initial side to the terminal side, that's your central angle, and it subtends 2 pi radians, then that angle would be 2 pi. So from here, I have a 0 radians all the way around to where it would be 2 pi radians. Now we can take this symmetry of the circle that's centered at the origin and then actually break up fractional pieces of that full rotation of 2 pi radians. So if I go not all the way around the circle, but halfway around the circle for my subtended arc, then my central angle would have a radian measure of half of 2 pi, which would be pi. Now remember that when I had a circle centered at the origin and it was in degree measurements of the angles, if I go all the way around, it's 360 degrees. So if I went half the way around, it's 180 degrees. So we get this relationship that pi radians is the same as 180 degrees. And that will be something that just will be an easy conversion factor to use later on. Before we do that, let's get to some other ones. So if I'm going from the initial side of the trig angle in standard position and halfway along the top half, not all the way to pi, but halfway to pi, that would be pi over 2. So 90 degrees is the same as pi over 2 radians. If I go 1/2, 2/2, 3/2, I have 3 pi over 2 for what would coincide with the degree measurement of 270 degrees. And we have the positive angles and the negative trig angles of radians just like we did for degrees. So if I had a positive trig angle in standard position that went from the initial side down to my central angle subtending this arc of 3 pi over 2, then that 3 pi over 2 angle is coterminal with an angle that starts at the initial side and goes down and around to hit, well, that would just be down and around to a pi over 2. Remember, the negative is the down motion, and if I'm just going down and around just a 90 degrees, which corresponds to pi over 2, that's coterminal with a negative pi over 2. So when we look at our radian measurement, if you have an angle x in radians, and you add multiples of, integer multiples of 2 pi, those will be coterminal. So x in radians, and you add to it integer multiples of 2 pi, you will get coterminal angles. Let's cut this up a little bit more, and then we'll look at how to change from degrees to radians and radians to degrees. So what's halfway between 0 and pi over 2? Well, halfway between 1 or 0 and a half is a fourth. So that would be pi over 4. So pi over 4 goes with a 45-degree angle. And you can count like fractional values as you go. So this is pi over 4, a fourth of a pi. Pi over 2 is a half of a pi. If I do the arc that does 1/4, 2/4, 3/4, this would be 3 pi over 4. And then 4/4 would be pi. Then add another fourth to that. From the initial side all the way around to this terminal side, that would be 5 pi over 4. Then 6 pi over 4 would simplify to 3 pi over 2. And then we would have our 7 pi over 4. And then 8 pi over 4 is back to 2 pi. And we're going to cut it up one more time in sixths and then simplify as we go. So if I take my pi and split it up into sixths, a sixth times pi is pi over 6, and 1/6 is smaller than 1/4. So it will have a shorter arc than the pi over 4 did. So here's my pi over 6. Then 2/6 is simplifies to 1/3, so 1/3 of a pi. So that's pi over 3. So 1/6, 2/6, 3/6 is pi over 2, 4/6 is 2 pi over 3, 5/6 doesn't simplify, that's 5 pi over 6, 6/6 of a pi is pi, 7 pi over 6 doesn't simplify, 8 pi over 6 is going to give me 4 pi over 3. 9 pi over 6 simplifies to 3 pi over 2. 10 pi over 6 simplifies to 5 pi over 3. 11 pi over 6 doesn't simplify. And then 12 pi over 6 simplifies back to 2 pi. Now that's as close as we're going to, or small as we're going to cut it up when we look at what are considered our nice angles. And our nice angles in our radians are what we have listed here. And again, remember, you can go up and around for positive angles, down and around for negative angles. And notice as you're looking through these, I should move this pi over 2 a little bit closer to the y-axis. When you're looking at these in terms of the values that are here, these are the angle measurements. We haven't done anything with the trig ratios of these angles. We're just doing the angle measurements first to get comfortable with that. And we've listed them as the positive angle measurements, but if we go down and around, you do the negative, but then you count your fractional values as you go of the fractional pieces of your sections of your circle when we work through this. Now, how do we go from radians to degrees and degrees to radians? Well, we saw some that we could just visualize. But really what you're doing when you go from degrees to radians and radians to degrees are just using a unit conversion factor in order to switch it. So remember, with unit conversion factors, they have the value 1. And they have the value 1 such that in the fraction, the unit you need to get rid of, you want to have in the opposite part of the fraction as where it currently is, so they cancel out as common factors. And then the unit you want to bring in the other part of the fraction, whichever it goes. So if I wanted to change 90 degrees to radians, and I'm picking this because we can already see what we're supposed to get. A 90-degree angle is pi over 2. I know I'm supposed to get pi over 2. So at least I can have a double check to see if I'm doing it right on this before I go do ones that aren't as familiar. So I have 90 degrees right now, and I'm going to put that over 1. I don't want the degrees, I want the radians. I have a relationship that's equal right here. Pi radians is equal to 180 degrees. They're equal. So if they're equal, if I divide them, it gives me the value 1. So for example, 2 is equal to 2. So 2 divided by 2 is the number 1. 12 inches is a foot. So 12 inches divided by 1 foot is the value 1. So if I have equal quantities and I don't have 0 in the denominator of the fraction and I'm dividing them, it's really just the number 1. And when I multiply anything by the number 1, I don't change its value. I'm just changing the way it looks cosmetically. So here, I can multiply this by the conversion factor where, well, the degrees are in the numerator right now, and I don't want degrees, I want radians. So if they're in the numerator, I have to put the degrees in the denominator to get them to cancel. And I know that 180 degrees is worth pi radians, so that's why I put, getting rid of the degrees, I put a 180 down there, and its equivalent is pi radians. And now I can just multiply across the top, multiply across the bottom, 90 degrees times pi over 180 degrees. And then remove common factor pairs. Well, 90 degrees divides into 180 degrees 2 times. So I get that it's pi over 2 radians. Exactly what we knew we were supposed to get. So if I want to go from degrees to radians, I take and multiply so that the degree measurements will cancel out. I multiply by pi over 180. What if I want to go from radians to degrees? So let's say we want to go from 5 pi over 6 to degrees. Well, I have my 5 pi over 6, and I'm going to multiply it by, I have radians right now, and I don't want radians. So I want to have the radians cancel out as common factor pairs, and so I need to have my pi radians in the denominator and my 180 degrees in the numerator. Multiply across the top, multiply across the bottom, and then remove any common factor pairs. I would have the common factor pairs of pi would remove, and then 6 divides into 180 degrees 30 times, and 30 degrees, and 30 times degrees times 5 is going to give me 150 degrees. Now be careful, if you have a radian measurement that doesn't have a pi in it, you certainly can have that. So if you had the radian measurement of, say, 2.3, and it doesn't have a degree on it, it's assumed to be radians. So here's just a quick thing to be careful about. If you mean the angle to be degrees, because that's what it is, you have to put the degree on it. If you have an angle that's in radians, be careful not to put the degree on it, because you need to make sure it's in radians. Radians can either have pi's or they might not have a pi. It just depends on the measurement. It's a real numbered value. So even if it's 2.3 radians and they want me to go into degrees, I have to get rid of the radians and bring in the degree measurement. So I actually want to go through and multiply across the bottom, and then get our degree measurement with the value divide by pi, and then whatever I have for that being the exact value, and then I could approximate it from there.